Imagine a future, right, where we can solve problems that are just completely impossible for today's supercomputers. Think about things like precisely figuring out the energy states of complex molecules, something absolutely crucial for chemistry, for materials science. That's really the incredible promise of quantum computing. But okay, if they're that powerful, why aren't quantum computers already everywhere? Why aren't they changing everything right now? The messy truth is that the hardware we have today, what people call noisy intermediate scale quantum or NISQ devices, well, they're prone to errors. Powerful, sure, but delicate.
Exactly. And the core challenge, it isn't just about scaling up, building bigger quantum computers. It's maybe even more about making the programs, the quantum circuits they run, as efficient as possible. And just to be clear, we're not talking physical wires here. A quantum circuit is more like a detailed recipe, maybe, a sequence of operations quantum gates applied to the qubits. The problem is every single one of those operations, every gate has a small chance of failing, of introducing an error, and those tiny errors accumulate really quickly. That's why making circuits shallow, meaning using fewer operations, is just absolutely vital if you want to get practical results from today's NISQ machines.
Right, getting the most computation done before the errors pile up too high. And that exact challenge, that quest for efficiency, is what we're really diving into today. Softbank recently put out this really interesting study looking at how to make these quantum circuits more compact. So our mission here is to figure out how this search for compactness is affecting the actual usability, the accuracy of quantum computers available right now.
Okay, so to really get into it, we need to talk about a specific algorithm called quantum phase estimation, or QPE. It's a cornerstone algorithm for calculating those ground state energies we mentioned, super important for chemistry applications. But here's the catch. To get more precise results with QPE, you fundamentally need more helper qubits, these ancillary or ancilla qubits.
Okay. So you need more ancillas for better precision.
Yes, but adding more ancilla qubits makes the circuit depth, the number of steps, and the total gate count grow exponentially.
Exponentially. Wow. So that makes it incredibly difficult, maybe even impossible, to run on current hardware.
That's it, exactly. It's this fundamental tension, this trade-off. You want more accuracy, but the hardware pushes back hard.
A real tug of war then. Precision versus, well, actually being able to run the calculation at all.
Precisely. And that's the dilemma the Softbank Research Institute of Advanced Technology tackled head-on in their study. They looked at this trade-off using hydrogen chain molecules. Simple systems, relatively speaking, but they're a really important benchmark in quantum chemistry. They had to translate the chemistry problem into a quantum one, of course. They used standard methods like the STO3G basis set and the Jordan-Wigner transformation. Think of those as tools to map how electrons behave onto the qubits. And crucially, for their accuracy benchmark, they used full configuration interaction, full CI. That's basically the gold standard for these kinds of calculations, so they had a very reliable target to aim for.
Okay. Sounds like a really solid, rigorous approach.
Yeah.
What about the quantum computer itself? What hardware did they use for the experiments?
They ran the experiments on Quantinuum's RAMI system. It's a 20-qubit machine based on trapped ion technology. And interestingly, this specific machine was installed on-site at Riken in Japan back in February 2025. It was actually the first time Quantinuum put one of their systems outside the U.S.
Oh, interesting. And what makes that hardware suitable for this kind of work?
Well, ion traps like RAMI have some key advantages. Things like full connectivity between all the qubits. Any qubit can interact directly with any other. Plus, they generally have long coherence times, meaning the quantum state lasts longer before degrading, and high gate fidelities, the operations are quite accurate to begin with. That all helps with managing errors.
Got it. So good hardware. Now, what about the software side? The tools used to actually build and shrink these circuits, what were they comparing?
They focused on three main software development kits, or SDKs. IBM's Qiskit, Quantinuum's own TKEA, and also Classiq's QMod platform. And they evaluated them very methodically based on three key things. How well did they compress the circuits? What did it cost to run the jobs? And most importantly, how accurate were the final energy estimates? They tested all this while varying the number of those ancilla qubits from just 2 all the way up to 6 to really see how things scaled.
Okay, the moment of truth then. How do these different SDKs actually stack up when it came to making the circuits smaller, more efficient? What did the results show?
Right. So first, let's look at compilation performance. Specifically, how many of those crucial 2-qubit gates, sometimes called CX or CNOT gates, were needed. Generally, the circuits generated using TKIT and QMod were more compact, required fewer 2-qubit gates compared to Qiskit. But here's where it gets really interesting. QMod, particularly when they used its flexible setting for handling parts of the circuit that repeat, showed significantly better compression as the circuits got bigger, meaning as they added more ancilla qubits. It scaled much better.
Okay. Better compression, fewer gates, especially for the bigger problems. That sounds good. But did that translate directly into lower running costs? You mentioned cost was another metric.
It did, yeah. On the Quantinuum machine, the cost is measured in something called hardware quantum credits, or HQC. And because QMod was able to reduce the circuit depth effectively, it resulted in lower HQC usage. So, yes, better compression directly meant cost savings. Just for context, they used, I think, about 1,000 measurement shots for the H2 and H3 molecules and 500 for the larger H4 molecule to get their energy estimates, so the cost savings could be quite significant.
Smaller circuits, cheaper runs. That brings us to the bottom line.
Yeah.
Accuracy. Did the more compact circuits actually deliver better results on the real quantum hardware? And you mentioned Qiskit earlier. Why wasn't it included in the hardware runs?
Good question. It's an important point. While you can technically take a Qiskit circuit and try to run it on Quantinuum hardware, it's not really optimized for it. Quantinuum machines have their own native gate set. There's specific ways qubits connect. Qiskit doesn't inherently target those optimizations, so running Qiskit circuits would give results, but they wouldn't be truly representative or fair comparison.
Okay, that makes sense. So they focused the hardware tests on TKET and QMod. What happened with accuracy there?
Right. So for the simplest molecule, H2, the results were really revealing. QMod's circuits actually showed better accuracy as they increased the number of ancilla qubits. More precision needed, more ancillas added, accuracy improved. TKET circuits, on the other hand, were accurate up to 5 ancilla qubits, but then the accuracy dropped off significantly when they went to 6.
Why the difference at 6 ancillas?
It boils down to the error rate on the actual hardware. The Ramai computer has a 2-qubit gate error rate of about 1.41 times 10 to the minus 3, roughly. What that means in practice is there's sort of an upper limit, maybe around 700 2-qubit gates, that you can execute before the accumulated errors just overwhelm the calculation. QMod's circuit for H2 with 6 ancillas, thanks to its compression, managed to stay under that approximate 700 gate limit. But TKET's circuit for H2 with 6 ancillas exceeded it. So the errors piled up and the accuracy degraded badly.
Wow, okay. So that 700 gate figure is like a practical ceiling on that specific hardware. And this is where things got even tougher for the bigger molecules, right? H3 and H4.
Exactly. Here's where the current hardware limitations really bite. For the larger H3 and H4 molecules, both the QMod and the TKE circuits, even after optimization, ended up needing more than that roughly 700 2-qubit gate threshold. And the consequence was pretty stark. The energy results for H3 and H4 just became unstable. They varied wildly. It really highlights that even with sophisticated circuit compression, we're still hitting the physical limits of today's NISQ hardware for problems of even moderate complexity.
So it paints a very clear picture of where we are right now. Even the best software can only do so much against the noise.
Absolutely. If we pull back to the bigger picture, this study really drives home a crucial point. The choice of your software tools, your SDK, isn't just a minor detail. It has a massive impact on circuit compression, on how many resources you consume, and ultimately on whether you get an accurate result at all. Selecting the right SDK, one that excels at compression for your target hardware, is absolutely critical for making quantum computations feasible and reliable on the machines we have today.
And presumably the benefits they saw here with QPE, better compression, leading to better feasibility, that likely applies to other quantum algorithms too, doesn't it?
Oh, definitely. The principles are broadly applicable. Efficient compilation, minimizing gate counts, especially those noisy 2-clip gates, that's going to be important across the board for making the most of NESQ computers.
It really feels like the software, the compiler, is just as important as the hardware itself right now. Maybe even more so in some ways, for getting practical results. So bringing this back to you, the listener, what's the key takeaway here? I think this deep dive really shows that the journey to practical quantum computing isn't just about building bigger, better quantum machines, although that's vital, of course. It's also hugely about the smartness of the software that makes those machines usable and efficient.
That's exactly right. You know, knowledge is great, but it's most valuable when you understand how to apply it. Seeing tools like Classiq QMod demonstrate this level of circuit compression, well, that's a really important step. It helps move quantum computing away from just theory towards actually getting useful things done on today's imperfect, noisy hardware. It really is about getting more performance out of limited, precious quantum resources. And looking ahead, the research isn't stopping here. They mentioned moving towards error-corrected circuits, right? Sounds like a whole different ballgame, trying to actively fight the noise?
Yes, error correction is the next major frontier, aiming to build fault-tolerant quantum computers. That's a longer-term goal, but essential for tackling truly large-scale problems. But even before we get there, there's always more to explore. And this whole discussion raises a really interesting question for you to think about. As the hardware keeps improving, maybe getting less noisy, maybe getting bigger, and as the software, like we saw today, gets even smarter at squeezing every last bit of performance out of these circuits, what currently unsolvable problems, what complex challenges in science or industry or medicine do you think might finally become tractable, say in the next 5, 10, maybe even 20 years? What breakthroughs could happen when we finally tip that delicate balance between needing high precision and having the practical ability to achieve it? Something to ponder.